Right, so I'm now going to record this revision quiz, which will consist of a certain amount of silence while you work out your answers. This is not assessed, and you don't have to tell anyone how you did. If there's time, we'll have a brief chance for questions at the end of the quiz, but I'm going to put a complete set of answers in full detail on the web. We'll have just brief summary answers today, and you may have a chance to ask me a couple of questions about them, but once the full answers are on the web, if you've still got any questions left after those, please feel free to contact me anytime. So, you don't have to justify your answers today. This is a rare exception in this module. Usually in this module you've got to justify your answers, and you've got to convince me with your justification. But today all you've got to do is write down the answers without any justification, just to make life easier and quicker. When you do have to justify things, your justification doesn't necessarily have to be long as I agree it's convincing. But part of what you've got to learn in this module is what will convince Dr. Feinstein. And that brings us to question 1, which is, what is the difference between a sequence and a series of real numbers? So I'll just give you a couple of minutes to think about what the difference might be. The rest of this quiz is going to involve quite a lot of mention of sequences and series, so if you can remember what the difference is, it may help. Okay, so question 2 is a question about sequences. Each part of this question, and I think there are something like 6 parts to this question, there's a particular sequence mentioned, and you have to decide whether you think it converges or diverges. And I'll give you for free that diverges just means that it doesn't converge. So diverges doesn't force it to go off in general to plus or minus infinity. It could oscillate around and it would still be called divergent, because divergent just means that it's not convergent. If you think the sequence converges, you should write down what you think the limit is. Here we go, we've got 6 of these. The first one is an easy one to get you started. It's just a sequence where xn is 1 over n. You have to decide whether it converges or diverges, and if it converges, what do you think the limit is? I don't think you need very long of that one. So move on to something that might look not quite as easy, but actually it's the sort of thing you did a lot in first year. So the nth term of your sequence has got numerator n squared plus 2n plus 3. The denominator is 2n squared plus n plus 1. It's just one polynomial divided by another. And as n gets large, maybe you can figure out what's going on there. You don't have to prove it today, but the way I would expect you to prove your answer will be in the model answers that I put on the web page. If it converges, what do you think its limit is? We move on to part C. Actually, I'll give you part C and part D together. Part C and part D are related, but they might be subtly different. So in each case, you take n plus 1 and do something to it, and then do the same thing to n and take the difference. In part C, you take n plus 1 and then you square it, and then you square n and you take the difference. And you get the square of n plus 1, and you subtract the square of n. Whereas in part D, you start with n plus 1 and square root it, and you take n and you square root it, and you take the difference. And so you're looking at the square root of n plus 1, and you subtract off the square root of n. And there might be a subtle difference between those two. So again, do they converge? Do they diverge? If so, if they converge, what do you think the limit is? In this module, infinity doesn't count as something you can converge to. You can diverge to plus or minus infinity, but you can't converge to plus or minus infinity in this module. It gets different in third year at the moment when you do measured integration, but that module won't exist by the time you get there. So there is a notion of converging to infinity that you meet later in analysis, but we don't do that. We don't do that this year. This year you can't converge to plus or minus infinity. Okay. Part E, you won't be able to work this out, I don't think, unless you can remember it from last year. 1 plus 1 over n is getting very close to 1 as n gets big, but it's being raised to the power n, which is a big power. So those two are fighting each other. A number that's nearly 1, that's only just a bit more than 1, being raised to a very big power as n gets large. Does it tend to 1? Does it diverge off to plus infinity? Or does it converge to some value in between? Or does it oscillate around? That's what you have to try and remember from last year. But I wouldn't expect you to be able to work that out on the spot, because it's not easy. Part F. If you try this on your calculator, you'll probably get the wrong answer. So n factorial on the top, 100th power, the nth power of 100 on the bottom. If you start looking at the first few terms on your calculator, it gets very, very small. But that might not necessarily give you the right answer. So does it converge or does it diverge? If it converges, what do you think the limit is? We now move on to a question on series. Now this time you don't have to work out what the value is. If it's a convergent series, and as you'll now discover, series involve summing infinitely many things. If it converges, you're not supposed to say what the value of this infinite sum is, but you are supposed to say which test you would use to be sure that it would have converged, or which test you used to be sure that it diverges. So, this first series here, is it a convergent series or is it a divergent series? Which test from last year would you use to try on it, to figure out what's going on? So the terms of the series that you're adding are minus 1 to the n over 2n plus 3. Now those terms are tending to 0, but you've got to add up infinitely many of them. So the fact that the terms tend to 0 might not be decisive, because you've got to work out what happens when you add them all up, whether or not you can even do that. You aren't asked what the value would be if you did add them all up, and if it did work. You just have to say which test you'd use. Second one then, you're summing infinitely many terms, and the terms this time are 2 on the top, 3n plus 4 on the bottom, 2 over 3n plus 4. Do you think that's a convergent series or a divergent series? Which test do you think you'd use to try to find out? Part C, that thing on the top there, it's the sine of n. So that's just sine of n on the top. On the bottom it's n cubed plus 1. Suppose you try and add up all of those. Can you do it? If so, how do you know that you can do it? You don't need to say anything about what the value might be, if it does sum. Fourth one, again an infinite sum from n equals 1 to infinity, and the terms are 3 to the n on top, n factorial on the bottom. Can you add those up? Is that a convergent series? If so, how do you know? Which test would you use? Can you remember the name of the test? And the fifth one of these, it's a bit like part A, but there might be a subtle difference. It's still alternating in sign, minus 1 to the n on top. This time your denominator, it's 2 plus 1 over n. So A and E are obviously similar, but there's some difference between them, and you might want to think about what that is. We now move on to the last question. This is a question about whether functions are continuous or discontinuous. And I'm just going to give you 3 different functions. And you have to try to decide whether you think they're continuous or discontinuous. You may want to try to sketch them, though that might not be that easy in all of the cases. But at least you might have some idea of what these functions might be doing. So the first one is the branch definition. That means that it's got one definition if x is greater or equal to 0, and it's got a different definition if x is negative. That's the otherwise. You'll notice that there may be something important happening as x approaches 0 from either side. So it's cos x if x is greater or equal to 0, it's x plus 1 if x is negative. If you put all that together and you sketch the whole thing, does that look like a continuous function or not? And a variant of that question, is it a continuous function or not? The second function is 1 if x is not 0, it's 0 if x equals 0. I should say that in future workshops you'll have an opportunity to talk to each other, and I don't really mind if you talk to each other for this quiz, come to think of it, but perhaps doing it yourself is slightly better, because give you a chance to see what you really do remember from last year. But there will be plenty of opportunities for you to work with each other in some of the other workshops. This one then is 1 if x is not 0, it's 0 if x equals 0, so there's just that one point where something strange happens. Does that mean it's continuous or discontinuous? And the final question, the final part of this question, which is the last question, this function is 1 if x is 0. Everywhere else it's sine x divided by x. So you have to think about that. It seems to have a strange value when x is 0, except that maybe it's an appropriate strange value, maybe it isn't. I could have put 0, I could have said 0 instead of 1. Have I made a good choice there by making it 1? That's what you have to think about. Okay, what I'll do is I will quickly run through those solutions, and then we'll have a break before the lecture. I'll give you an opportunity for a quick question as well, but I think it may be better for you to look at the full version of the solutions that's going to be on the web page. So we'll close this up. And we'll have the solutions. What's the difference between a sequence and a series? Well, as will probably have become apparent in that quiz, in a series you've got to add all the numbers up, or try to add all the numbers up. So there are actually very strong connections between a sequence and a series. But in a sequence you're not asked necessarily to add anything up at all. In a series you're going to be trying to add up infinitely many terms. So I think the description you got in first year is that a sequence is an infinite list of numbers, but you don't necessarily have to add them. But in a series, you've got to try to add them. So you're looking at an infinite sum of terms. So of course, the terms that you're adding form a sequence. But then when you add them all up, or try to add them all up, then you've got a series. So here's the answer to question 2. 1 over n converges to 0. The second one, the terms n squared and 2n squared are dominating as n gets big, and so it tends to a half. But the way I'd expect you to write that out, you'll see in the model solutions. And the difference between C and D is that if you square n plus 1 and then subtract n squared, then you get some of the diverges. Whereas if you use square roots instead, you get something that tends to 0. That's not particularly easy, and might be a nice exercise for you to try to do all the details if you haven't done it. But the full version will be on the web page. Part E is too easy to try, is too hard to try and do on the spot. It happens to be a standard sequence that converges to E, and it's something that was done last year. And if you don't remember why that is, it may be worth looking at. So it doesn't tend to 1, it doesn't go off to infinity. The two things that were fighting each other actually pretty much cancel each other out, and what you get is it converges to something strictly between 1 and infinity, namely the number E. And part F, no matter what your calculator tells you about the first few terms, eventually those terms start to get really, really huge. Once n gets to 1,000,000, that can be pretty vast. So that diverges. Now for the series, there may be more than one way to do each one. But I've put some warnings in here about some of the tests that you shouldn't try to use. If you're not sure about the test you tried, then you can ask me separately. So part A converges by the alternating series test. That's a perfectly good alternating series. Crucial thing to notice is that the terms are tending to 0 in this one, which is different from what happens in part E. Part B diverges using some version or other of the comparison test. I've mentioned one called the limit comparison test. If you look back last year, you'll find various versions of the comparison test you could use on this. But if you try something called the divergence test, it doesn't help you. So this one is the divergent series, but you can't use the divergence test to tell you. Part C, you should use a comparison test. The alternating series test isn't valid because although there are some positive terms and some negative terms, they're a bit random. The sign of n is wandering around a bit and it's not exactly alternating, so you can't use the alternating series test here. Part D converges by the ratio test, and part E diverges by the divergence test. So the difference between this one and the first one is if you look at the terms here, they don't tend to 0. 2 plus 1 over n gets close to a half, You've got a minus 1 to the n on the top, so after a while the terms are pretty much like minus a half and plus a half and minus a half and plus a half, but it doesn't tend to 0. And if the terms in your series don't tend to 0, then your series is always divergent. That's what the divergence test tells you. So you can't use the alternating series test unless you have a version of the alternating series test that covers cases where the answer is that it's divergent. The alternating series test is usually used, when it's valid, to prove that a series is convergent. Otherwise, you'd be using the divergence test. And for the last question, the functions f and h were continuous, but the one in the middle was discontinuous. And again, there'll be more details on that in the model answers. So we'll stop that session there, and we'll have a 5-minute break, and then we'll have the first lecture.